Hi, everyone. Thank you for staying till the very end of this session. My name is Ariel Miara. I'm a PhD candidate at the City University of New York, and I work at the CUNY Environmental Crossroads initiative. Today, I'll be speaking about climate change impacts and alternative water management strategies for the power sector, specifically talking about thermoelectric power plants. Just to quickly mention, this is my first AGU talk. And I was feeling a little nervous, so I asked my very wise advisor, Charles Vorosmarty, for some advice. And as my advisor, he advised me, I think maybe in the spirit of AGU, to have a couple of shots of whiskey before I speak. So if I slur any words, you'll know it's because of some very good advice. How do I move to the next one? Just click. Okay, I swear I really didn't do that. Oh, over here?
Where is presentation mode? I'm go to view, I'm sorry.
All right. Where is it? Okay, thank you. All right. Okay, so first, this is what I'll be talking about today. I'll give some background on the contemporary Northeastern U.S. electricity water nexus, so that hopefully we're all on the same page when I start speaking about the particular study, which is looking at future electricity expansion scenarios. I'll talk about the aim and approach to the study, the tools that we use to execute the modeling scenarios, and I'll show some preliminary results. Just a reminder, the domain is the Northeastern United States, looking from Maine down to Virginia. This is a good slide, I think, that captures the feelings and emotions of power plants. I first heard it when I was a newbie to the energy water nexus. Ashlyn Stillwell, who's now at the University of Illinois, mentioned this once in a presentation of hers. And the take-home message from this slide is that when it's too dry or too hot, which typically would happen in the summertime when we need electricity the most, power plant efficiencies can decrease. And when they decrease, it means that they may not be able to produce as much electricity as they may have hoped. A little bit more background about, so power plants are affected by climate and availability of water resources, but that also depends on the cooling technologies that they employ at the power plants. So there are two types of water use, water withdrawals, which is water that is removed from a natural water body, and then water consumption, that is water that is removed but then is not put back in the original water source. So the different cooling technologies are listed here. Just running through them quickly. Steam once through withdraws a lot of water and consumes a relatively low amount. Steam cooling tower withdraws less but consumes a large percentage of that water. Dry cooling does not use any water for cooling. And I put combined cycle power plants here differently. OT refers to once through, CT to cooling tower, DC to dry cooling. And the reason I put that separately is because natural gas power plants are more efficient than steam powered power plants. And because they're more efficient, they use less water. So just remembering that as we dive in. So for this particular study, the motivation comes from, as we've already seen in some of these talks, some studies, including ones that we've also previously done, show that climate change may increase water temperatures and decrease water availability in the summer, making electricity generation more vulnerable. And our aim for this particular study is to capture the dynamics between climate, water, and power plants, thermoelectric power plants, to see what the impacts might be on different scenarios, including business as usual scenario or a scenario with different water management strategies. And our approach was to link two models together. So the Regional Electricity Deployment System, REEDS, which Robin Newmark spoke about earlier, to a model that simulates power plant operations. And I'll speak about that more in the next slide. One of the important things to remember is that REITs forecast electricity expansion on a regional level, and it has 134 power control regions. And in the Northeast, there are 20 regions. Meanwhile, TP2M in frames, TP2M, if we go to the next slide, TP2M stands for thermoelectric power and thermal pollution model. So if you imagine, and it's pixel based, so if you imagine the points of where the power plants were earlier on the Northeast map, what TP2M does, it's a power plant simulation model that is embedded in a water balance model. So for each pixel where there is a power plant, the power plant can read or take in the information of how much water is available to it, the temperature of that water, and the air temperature as well, and determine what the efficiency is of that power plant. So we take information from reads and we downscale it to the power plant level. And there are about 380 power plants that we take into account in this study. And I'll talk about the downscaling in a little bit. But a couple other things to note is that as the power plants use the water, they also heat it up. And what this model is able to do is that it takes into account downstream impacts. So if this power plant was to take in cool water and discharge hot water as part of the impacts of the cooling process, another power plant downstream may also be impacted, and this model is able to take that into account. So these are the scenarios I'll be talking about today. We have some additional scenarios, but because of time constraints, I won't be able to speak about all of them. So the first scenario is keeping the contemporary electricity demand and infrastructure. So if we remember that map at the very beginning of the Northeastern US, it's basically keeping that infrastructure steady and the demand, the electricity generation demand that we have today steady through 2050, 2010 to 2050. A second scenario is a business as usual scenario that is modeled from reads. And the third scenario is a no new once through power plants. So the power plants that withdraw the most water are not allowed to have any new builds. The spatial resolution, so that we take the, as I mentioned, we take the results from reads and we model it through TP2M frames, which is at a 3-minute, which is a 5-kilometer grid cells. And we've modeled this under RCP 8.5 from 2010 to 2050. Just so that we understand what reads is forecasting and what the scenarios mean in terms of electricity projections. So today, we have a system that's heavily reliant on water resources with a lot of steam once through and steam cooling towers. The business as usual scenario shows a high increase in combined cycle once through. So that's a high increase in natural gas, which is one of the reasons I kept the cooling technologies a little bit separate. And then the third scenario, the no once through scenario, also has a large increase in natural gas, but this time it's with cooling tower systems. So those cooling tower systems withdraw less water but consume more. Now, as part of this study, we needed to come up with a way to downscale reads electricity outputs into an individual power plant level. So we had the outputs from reads, which are 20 polygons for the Northeast, and we had to decide how are we going to take into account increases in coal, for example, or natural gas. Where are we going to put those power plants? Are we going to add it to power plants that already exist? And so on, because depending on where you add it, so for example, if you added a power plant upstream or downstream of another power plant, you're going to be impacting the efficiencies of those power plants on certain river reaches. So we came up with a set of downscaling rules based on water availability, water temperature, and generator sizes. So I'll go through an example of this downscaling quickly. So we start off with the summer average discharge. And we look to see where the potential coal power plants with cooling towers are, for example. And we see that multiple river reaches can accommodate coal power plants with cooling towers. Now, when we move through to looking at the potential for coal once through power plants, we see that because they withdraw more water, there's a lot less potential room for them to be built, less potential, less river reaches. And just to make sure that our methods and our calculations were accurate, we look to see where today's coal power plants are with once through, and we see that they do indeed lie on these river reaches. So again, it's important to take this into account when building new power plants because you might affect one's upstream or downstream. So looking at the climate impacts on water resources, this slide shows increases in water temperature, which is sampled at the power plant location. So looking only at grid cells for where the power plants are, we see that there is an increasing trend in water temperature. Now, when we look at water flow, so water flowing through those grid cells with the power plants, we see that there's a decreasing trend. So what happens through time is that we see basically more instances of high temperatures and low flows. And if we remember before, that area of the Goldilocks nexus where you had, if it was too hot or too dry, power plants would get impacted. They would have lower efficiency. So just keeping that in mind. So this is the space where we'll be comparing the scenarios, comparing the electricity generation potential from those different scenarios. 100% means that is the demand. It's the generation that's projected from reads. So if the power plants are able to meet that, you'll see a line that goes all the way across. We'll be looking at the percentage attained of those power plants. How much of the generation that reads is asking for is able to be attained. So first we're looking at scenario 1, what would happen if we kept today's electricity generation and infrastructure, and we see that slowly as we have less water flowing through the grid cells where the power plants are and higher temperatures, we get lower and lower generation output from those power plants. And just to put this in reference, 10% here is about 15 500 megawatt power plants running for 24 hours throughout the whole summer. And just a reminder, this is looking at summertime electricity generation. Now, if we look at the business as usual scenario, we see that there's a little bit of improvement because natural gas combined cycle power plants require less water, but because it's once through, you still get some impacts and you still get the decreases when there's not enough water or when the temperatures are too high. Now, the third scenario, where we have no new once through, we can see there's a much larger improvement because these cooling towers taking less water and are not as reliant on the water temperature for their efficiencies, they're able to generate more electricity than the other scenarios. But an important thing to consider is that, yes, they withdraw less, but they consume more. So when looking at other regions that might not have as much water resources available, this may not be a feasible option for water management. And then another thing to note quickly is that at the beginning, the cooling tower scenario actually generates less because cooling tower power plants require more, they are less efficient than once through. So at the beginning, you see that they're able to meet less of the electricity, but through time, they are actually able to meet more because they require less water. And I'm running out of time, so I'll skip the summary and leave it there. Thank you. Questions? Yep.
Just a question on the relative effect of temperature and flow in your model.
Mm-hmm.
I think the bulk of climate models project increases in precipitation over the Northeast.
Yep.
I'm just wondering if you had that kind of trend instead of a decreasing trend, what your results might look like.
Okay, so That's a very good question and something we've actually been looking at. So yes, in the Northeast you get more precipitation, but that doesn't necessarily get reflected in the amount of water that's flowing through your rivers. So for example, you might have high precipitation, but your evapotranspiration rates might go up because your air temperature is really the determining factor in seeing how much discharge you have in those rivers. So maybe previously, before we've had such climate impacts, we've seen that precipitation has been the main driver of how much water is in the rivers, but going forward, air temperature really becomes the dominant factor. Yep.
Could you describe the stream temperature modeling and how you came up with those projections and what climate scenario?
So this was climate scenario RCP 8.5. We've taken ICIMIP data, so air temperature, humidity, cloud cover, wind speed, and the river temperature model is based on a Dingman model from New Hampshire, and they look at basically interchanges with, if I go back, yeah, no, I didn't have time for that, but so yeah, it takes into account air temperature and impacts from solar radiation and that kind of thing, and calculates the river temperature for a particular grid cell, and then looks at the downstream length and depth of the river to yeah, it's a physical model. Yep. That's it. No more questions? Okay. Thank you.